Yeah, well, thank you. I'm happy to be given a chance to tell you about what we do in Kvasir in this ShippingLab project. My name is Joachim Bachmann Nielsen. I'm one of the co-founders of Kvasir Technologies, and my background is in research and chemical engineering. Firstly, let me briefly introduce you to Kvasir. Kvasir is a spin-out company from the Technical University of Denmark, founded in 2018. And we have since then attracted seed funding together with various grants, including grant funding under this ShippingLab project currently ongoing. We are today co-located with Alfa Laval in Søborg, Denmark, where we currently occupy 200 square meters of factory space, as well as some office space. We own IP on our own novel method for liquefying biomass into a sustainable ship fuel. IP protection is integral to our business model as a future technology supplier. Last year, we also incorporated in the US, where we currently have one guy working, assisting with collaborations across the Atlantic, and most notably an ongoing collaboration we have with Iowa State University, which is directly co-sponsored by this ShippingLab project also. I would also like to line out what our process technology covers. We basically replicate the natural process of turning biomass into oil. Rather than taking millions of years, we like to say we do it in minutes. Our proprietary technology is capable of converting basically any plant biomass, the non-edible components known as lignocellulose. That could be everything from agricultural waste and residues such as straw to wood chips. And we're even capable of converting the part of biomass known as lignin. For this reason, our technology is feedstock agnostic, which means that we will be able to supply a highly scalable oil product supply in the future, produced anywhere in the world where farms and forests exist. Our process technology is known as solvent liquefaction, and we are currently the only one in the world attempting to commercialize this specific technology where we use alcohols as solvents. And we basically subject the non-edible biomass to a pressurized cooking in an atmosphere of either ethanol or methanol. The alcohol is only lost to a limited extent, as the majority is recycled in the process. But during the reaction conditions, the biomass is broken into smaller fragments in what is called depolymerization. But these fragments tend to be very reactive and have a tendency to recombine and form disadvantageous char product. We just heard that char is also advantageous, but we want to focus on oil yields for our process. This is well known from other thermal liquefaction technologies such as pyrolysis and also hydrothermal liquefaction. But the presence of alcohol in our process, it is the secret sauce. It helps inhibiting these recombination reactions, resulting in a high liquid yield of highly stable oil product with substantially reduced oxygen content. And all that is under the right conditions without the use of catalyst and hydrogen. The oil product, as mentioned, is uniquely stable, which effectively means that it can be stored for years without degradation, which is highly important for long journeys at sea. And the oil can even be reheated without degradation. And this is due to the low oxygen content, which also gives it high energy density. It's actually comparable to fossil fuel, even without the use of catalytic systems and refinery-like hydrogenation. Ultimately, the oil is also sulfur and acid-free and can therefore be used as is for maritime shipping. So in summary, we are targeting a drop-in quality biofuel for shipping, since we believe it's the best solution is to change the fuel rather than changing the big expensive engine on board large ships. And in Kvasir, we work together with Norden, who has also expressed willingness to conduct the first testing of our fuel on board one of their existing vessels, and they're directly a partner in our ShippingLab project. And this will be unfortunately only carried out after completion of the ShippingLab project, since during this project we will not reach the scale of volume needed for this testing. So we're one step behind MASH in that regard. This slide further summarizes some of our fuel specs and shows that we can make biofuel product that in many ways is comparable to HFO, but without the negative effects of sulfur and CO2 impact. The ShippingLab project is called Biofuel Oil, BFO, a scalable and sustainable drop-in fuel for shipping. And the objective is to further develop this drop-in biofuel technology by proof of scalability, which is continuous production, and then evaluation of product quality and process economy. And here the main aspects of the process design are drawn up without going into very great detail. And we work on combining the aspect of feeding on the left, which is the biomass and the alcohol slurry, into a reactor, which is in this case basically a heated pressure vessel, and then the further downstream separating and recovering the oil product. And all of this combined in a continuous fashion, meaning that biomass is fed continuously in one end, while oil can be conducted continuously in the other, will help demonstrate proof of scalability, since batch mode processing commonly used in the lab is not industrially applicable and scalable. And furthermore, such continuous testing allows for larger volumes to be collected, which will help us further evaluating the oil quality with the help of our partner Norton. And in combination, the whole thing can be used to validate energy and process economics. And this leads to the first challenge in designing a scalable process design. Because very high pressure is in this context a potential scale-up barrier. Since we operate at elevated temperatures, upwards of 400 degrees C, this requires the steel to be used of a certain thickness, not least of much more expensive alloys that can withstand the rather aggressive conditions of supercritical fluids. So lowering of pressure is the single most effective way to effectively lower capex and thus production costs. We have managed to reduce the reaction pressure from initially in excess of 200 bar down to less than 50 bar. And we estimate that that alone is a cost saving of more than 50% in terms of capex. And we actually found out by investigating the effects of reduced addition of alcohol to the process. And it turns out that we do not need as much alcohol solvent as originally anticipated, which luckily not only reduces pressure and thus capex, but it also happens to reduce OPEX. And it turned out that since we were able to drop the reaction pressure to below 50 bar, we were able to identify a pre-existing pilot cell suitable for running our process. The initial intention was actually to build and test the process continuously in-house by ourselves, which was already delayed due to COVID, so this was really strike of luck. That we now have an ongoing collaboration with Iowa State University, the owner of this pre-existing pilot setup that we're using. We expect to have the final results here from before the end of the year, hereby effectively validating the process design by continuous production. And it will also aid in validating oil quality due to being able to produce several liters at the time for more extensive testing, both externally as well as for in-house lab tests. And this pre-existing pilot is the result of a former joint venture between Chevron and Weyerhaeuser, known as Catchlight. Some of you might have heard of it. The process that they used was slightly different in that different solvents were used, but operating conditions were strikingly similar to our needs. Obviously, working with low boiling alcohols has imposed some added challenges in terms of handling these substances with fairly low flash points. And that is also the main reason for some of the modifications to be carried out are mainly safety system and more extensive and excessive cooling in case of leakages. Iowa State University is also a distinguished university in the field of biomass research, so we are happy to have been able to facilitate this collaboration under ShippingLab. While reducing the amount of alcohol needed to reduce the pressure, solved one challenge, it also imposed a new challenge. How does one most efficiently handle high solid content slurries in a pressurized heated system? Our in-house work in the lab had always dealt with piston pumps, which are easy to control and relatively cheap, but we kept seeing solids build up near the pump exit with very high solid loadings. And that can also be seen here as illustrated on the leftmost picture. The pilot testing in Iowa, it does solve this issue by using a twin screw extruder as a pump device. And while that is indeed a very suitable way of pumping lots of solids against a high pressure, the solution is really finicky in that a pressure seal is highly dependent on the feed composition. But worst of all, this is not a scalable solution. You can't just make it bigger. So while we will be able to demonstrate the scalability of our process, we cannot scale the pump. Therefore, we are already in dialogue with various pump suppliers, and we are, in this regard, heavily inspired from pumping of high solids content slurries from other industries, such as construction. And we are also scheduling pump testing in parallel with the pilot testing, since luckily one can easily simulate the conditions of operation externally. We're already working on projections for a demo scale facility using the process design and input from our piloting in Iowa. And our preliminary projections indicate a production cost of our fuel of less than 600 euro per ton, which is pretty good. And this will, of course, be updated iteratively as we get more and more accurate data from Iowa. It is the ambition to leverage these piloting results obtained under the ShippingLab project to conduct the necessary engineering for a demo plant. We have identified some promising locations for a future first-of-its-kind scale facility here in Denmark. Such facility would then use straw as a feedstock. We estimate from such a facility that the annual production will amount to 10,000 tons of biofuel per year from some 25,000 tons of biomass. In summary and in very simplified terms, this is what the overall balance looked like for a first-of-its-kind production facility. Energy balances based on current data indicates that the process can be driven entirely by internally generated process heat due to the formation of flammable gases in the process. And as can be seen, the amount of alcohol required is rather modest in comparison to the amount of biomass. And this is basically makeup solvent that is shown, since the majority is recycled internally and therefore not visible on this diagram. The ambition is to use all of the bio-oil produced as a ship fuel, but we do also look into the fractionation of this oil, and in this case possibly serve other markets than strictly maritime. Solid residual char byproduct is likely suitable as a soil amendment. We are increasingly looking more into the value of this byproduct, as we've just learned from Jakob that it can really play a key role in obtaining CO2 negative biofuel due to the ability to sequester carbon this way. CO2 is also directly produced in our process, and in the context of carbon sequestration, it is also highly interesting that such high quantities of CO2 are actually produced on site. It turns out that CO2 is actually the main way in which oxygen is expelled from the biomass in the process, and thereby yielding an oil product with reduced oxygen content. And not directly part of this ShippingLab project is the integration with Power-to-X. It is, however, very convenient that we could potentially obtain the alcohol we need for the process in the form of methanol from CO2 in an integration with Power-to-X. As a matter of fact, our process would thus contribute to an excess production of methanol, which is conveniently also a potential green ship fuel. And with that, I'd like to thank you all for your attention, and you're very welcome to reach out to us after this presentation. I'm always very happy to have a cup of coffee, both virtually or in person, at our site in Søborg. My contact details are shown here, and thank you.